Right, so as we do the problem, I'm going to save this video, so hopefully this is sufficient. Of course, Canvas is going to store this recording for the next 2 weeks, so you can look at this video in Canvas for the next 2 weeks. Alright, so let us do now some few math problems. So we'll begin with this kind of problem. So you have, say, a TCP session going on between a source and destination, and these are the four parameters that I said we will be storing in addition to the buffer space. So the maximum receiver buffer size at the receiver side is 30,000 bytes, and the parameters last byte acknowledged at the source is 20,000 bytes, last byte sent at the source is 30,000 bytes, last byte read at the receiver by the application running at the receiver is 1500 bytes, last byte received at the receiver is 20,000 bytes, and the sender has also estimated the congestion window to be 15,000 bytes. So now what we want to estimate is how much more the sender could send, which is called the effective window size. Now we need to compute this considering all the three, which means only congestion control, only flow control, and both flow control and congestion control. Of course, in the real world, we do both flow control and congestion control, but for theoretical purposes, we should be able to also do the math by considering only one of the two. So let us say we consider only the congestion control. That means we are discarding the advertised window size. So again, each time we want to measure the effective window size. So the original formula is this: the minimum of the congestion window size and advertised window size minus the outstanding bytes, which is the last byte sent minus last byte acknowledged. Now when you discard the advertised window, it is simply then the congestion window size minus the outstanding bytes. So the congestion window size is given as 15,000 bytes in the problem, and these two parameters are given as 30,000 for the last byte sent and 20,000 for the last byte acknowledged. So you look at the table that is given to you. So last byte sent is 30,000, last byte acknowledged is 20,000 bytes. So the outstanding bytes is the difference between the two, which is 10,000 bytes. So what is the effective window size? So the sender has estimated that it could send 15,000 bytes of data to avoid congestion in the internet. And out of that, it has already sent 10,000 bytes, which are the outstanding bytes. So the balance it could send is 5,000 bytes. So that's all it is. That's the effective window size based on congestion control alone. Now, based on flow control alone, that means you are discarding the congestion window size in this formula and taking just advertised window size into consideration. Now, if you look at what the data given in this problem, the advertised window size is not directly given to you. You are given the maximum receive buffer. So that is the maximum buffer space available at the receiver side, which is 30,000 bytes. So we have to calculate the advertised window, how much more the receiver can receive and store. Now the receiver has received up to this bytes in order. That's the last byte received, which is the notation D, that is 20,000 bytes, minus the last byte read, that is 15,000 bytes. So it is buffering the difference, which is 20,000 minus 15,000. So it has buffered 5,000 bytes of data in the buffer of space 30,000 bytes. So what is the receiver advertised window is going to be this maximum buffer space 30,000 bytes minus this 5,000 bytes of data that has been buffered. So that 5,000 is calculated based on the last byte received minus last byte read. So the advertised window is 30,000 minus that 5,000. So that is 25,000. So that is the advertised window for the receiver. So the source gets to know that using an acknowledgement packet, as you saw in the earlier examples. So the advertised window is 25,000 minus now the outstanding bytes. So outstanding bytes, again based on the source point of view, it is what you have sent minus what has been acknowledged. So 30,000 has been sent so far and 20,000 has been acknowledged so far. So the remaining is 10,000 bytes of data are still in transit. So they're called outstanding bytes. So the advertised window of 25,000 minus the 10,000 is 15,000 bytes. So this is the effective window size, means the amount of data the sender could send furthermore beyond what it has sent so far and not yet acknowledged. Okay. So now we have to consider both flow control and congestion control. So that means we have to take the minimum of the congestion window size and advertised window size. So the congestion window size in the first part of the problem we estimated or it's actually given as 15,000 bytes, and the advertised window is what we found out from the second part as 25,000 bytes. So we take the minimum of 15,000 and 25,000, which is 15,000 bytes, minus the outstanding bytes, last byte sent minus last byte acknowledged. So 15,000 minus 10,000 is 5,000 bytes, is what is the effective window size, what could be sent furthermore. Okay. So you could see here actually this 5,000 bytes is the number also we got by considering only congestion control. So so even though we say we do both flow control and congestion control, we in the formula you can see we take the minimum of the congestion window size and advertised window size. That means eventually we are going to do we are going to send based on the flow control problem or based on the congestion control problem, whichever is the bottleneck. Okay, so typically with the resources available at the host machines these days, flow control is not an issue. So congestion control is typically the bottleneck that will decide how much more the sender can send. Okay, so with this let me stop and save this video.